Hopefully I make myself clear in the previous video or the touch-up. Okay, so let's continue with the axial stiffness. Alright, the axial stiffness equation. So previously in the previous two videos ago, we do all the necessary stuff to calculate our Qij woven roving. Alright, where we acquire the values, which is being shown over here. Okay, which is all these values. So I'll just make things neater so yeah, at least you can see it properly. And I have these values all along here. Okay, so if you take a look in our axial stiffness matrix, I should say that this is actually our step 7 now. Alright, if you were to compare it back to the previous part where we last actually stopped. Alright, this is the last step. Previous step was the 6th step. So let's talk about the 7th step now. Alright, in order to calculate our axial stiffness. The axial stiffness utilizes this summation of all the Qij bar. Alright, so what it means is that you're talking about summation of all the laminate. Alright, this is a summation of all the laminate. If you think about it, our question, alright, the question says that both laminates are running at angle theta plus minus 45 degrees. Alright, so your laminate, there is actually two laminates. Alright, one is in the negative 45, another one is in the 45 degrees. Alright, so there is two laminates. Alright, and we know that, don't forget, in the previous video we say that minus 45 or plus 45 degrees, they are the same. So you must, alright, write it down that this particular values, alright, when theta is equals to 45 degrees and also is equals to minus 45 degrees, you must say that. Alright, please take note of that. Okay, and therefore knowing this thing, we know that we have two laminates. Alright, so in other words, we have 2 times of this. Alright, so in other words, the summation of, because k is the number of ply, we have 2. Alright, so therefore we are summing out all the Qij bar WR plus all the another Qij WR bar. This is for the 45 degrees plus the minus 45 degrees for this case. Okay, so this is just the summation. Alright, this is only for the this angle, this is for this angle. Alright, so you are summing out all the stiffness matrix of your what? Sandwich panel. Alright, to be more exact is the faces of it. Alright, this face. So this face, each of them has 2 laminate. Alright, so currently what I'm calculating for this axial stiffness thing is only calculating for one of the face only, this face, that's all. So this face itself has 2 laminate. Alright, then hopefully you can see there's 2 laminate. One is at this angle, the bottom one is at like this angle, and nonetheless both of them are woven roving, and this is why they're like that. I don't know whether you understand what I mean in the future, but anyway, so because this is unidirectional, right? However, we are woven roving as the word suggests. Alright, therefore it's like this. So both of the laminate is like that. Okay, hopefully this is pretty clear. But coming back to this thing now, this portion over here, as we say, is a summation of the 2 laminates, which we have done for the woven roving, and then multiply with h. H is the total thickness of your laminate. So what is the thickness of your laminate then? Head back to this diagram, figure 2. Alright, your beam is, if you still remember, we are doing beam. Alright, we are doing a beam. Okay, so this thickness is actually the this face thickness, the thickness of the face, which is actually 4, right? Because if you think about it, this is 12 minus 8, you'll get 4 over here. This is 4, right? So therefore, your h is equals to 4, alright, divided by the number of plies, which is 2, okay? And therefore you have 2 times 2 of this thing, alright? Say my fault, alright? Because this should be 2 cm, this should be 2 cm. So 8 plus 2 plus 2 is equals to 12. So therefore my fault, the thickness of the laminate or the thickness of your face should be 2, okay, because this is the total thickness of your laminate. Alright, so it's talking about this thing, right, as we have said, but actually this is 2. I don't know whether 2 cm or whatever, but it's unit of 2. Alright, so this is also unit of 2, so take note of this careless mistake. But anyway, so at least we know that we are there. So this 2 and this 2 will cancel each other, we will have equals to 1. Alright, so so we will have 2, because this thing and they are the same, so this thing plus this thing is equals to 2 times of the QIJ bar, or of the woven roving. Hopefully this is pretty clear. For AIJ is equals to 2 times your QIJ woven roving. Okay, so if I were to write it in terms of matrix, it's just simply writing them down already. Alright, so A11, alright, A11 will be equals to 2 times your this one, right? 2 times of this. So it's 36.785 times 2 is actually okay. So this thing over here is your 2 times of your QIJ, alright? So this is actually your Q bar 11, which is in the end is A11 bar woven roving. Alright, so if I were to just, I think it's straightforward already lah, alright? So this value is 2 times of your Q11, right? This thing also here is 2 times of your Q12, same thing for your Q12 over here. Q22 is 2 times of this. Q33, sorry. Yeah, Q33 is this. Hopefully this is all clear to you lah, alright? But nonetheless, if I have to label, then if happen that you want to make it more clearer, that will be better. Okay, so you have finally found our axial stiffness, alright, but yet we are alright, we are still long away from our answers. But just to double check, where are we now? We are at the calculating axial stiffness, and we are at the last step of the first part. Alright, so we are going to find the longitudinal Young modulus, Eox. So where's the Eox formula? Alright, so your Eox equation is this one, you should be able to memorize. So it's just subbing in only A1, A2, so we have all those values already. And if you have to just sub it in, this thing, okay? And in case you may wonder why is it A12 this value, why is it same as this? This should be A21, right? You may wonder. Because in a stress system, alright, A12 are the same. Alright, this is in the stress system, A12 are the same. Okay, if I were to calculate for this value now, alright, my answer would be I would have 13.07 GPa. Remember, these are all in terms of gigapascal, in case you may forgot. Alright, because this is your Young modulus equation. Alright, your Young modulus is in terms of gigapascal type of thing. Alright, be careful of all the units lah. Alright, so in this case we are quite safe that it's all in terms of giga. Just to let you to take note that the lecturer's answer is actually 10.8. Alright, because he rounded up quite a lot of stuff, and I kept the decimal points quite well all along. So it depends on how you do it, but the range is somewhat the same, or somewhat about this gigapascal. And therefore this is the Young modulus. Alright, this Eox, this is your Eox already. Alright, your Young modulus of your laminate, or your 2 laminates. Alright, so if you were to come back here, this is the faces, this is the core. Alright, so you have found the Young modulus of these 2 faces. Okay, then I'll just color it now. Alright, so these are the Young modulus for these 2 faces, which is 13.07 GPa. Okay, and just a recap, we have somewhat reached here already. Okay, so we have found this thing, Eox. Alright, and the purpose of us getting this is that we are trying to use this value to get our shear stress. If you remember, our objective is to determine the maximum shear stress interface between the core, this is the core, and the faces. So this is the interface between them. So you are trying to look at the shear stresses of them. Alright, look at the shear stresses you need. Alright, your Young modulus of your face and the Young modulus of your core. And this is why what we are doing all along is to calculate the Young modulus of your face, which is a very big part. Alright, so once we get this, then we can sub it into this formula, which is to get our shear stress. And therefore in the next video we will talk about how to use the formula and eventually to get our shear stress then. See you!